Hi, this is Yours Peels, and this is another edition of 3D Printing News Unpeeled, courtesy of 3dprint.com. So today we've got a couple of news items for you today, and we're really looking at the top news in additive manufacturing 3D printing for the day. The first one is Stryker has a new interbody fusion system, interbody system. This is the Monterey AL, which uses its titanium technology. It's an anterior lumbar interbody fusion system meant to mimic cancellous bone, of course, in a sense. And what Stryker has managed to show in a bunch of papers and demonstrations and things is that it's better at bone generation fusion in this particular instance, using this kind of bone adhesion geometry that the company uses with as created through 3D printing. What they also have done this time is they allow this particular product allows for a deeper positioning and fixation and easier access to fixation in the back. So they really looked at this ergonomically. And they really have said in a separate statement that they want like more intuitive instruments. And I really like this approach. And we have to understand that Stryker is really the leader in this additive space as far as orthopedics is concerned. And now orthopedics are moving from acetabular cups, the knee replacement, and to spinal fusion, and a lot of other systems as well. There's a lot of startups and there's a lot of approvals in this area, and there's a lot of companies entering this area, either developing new products or kind of developing new kind of versions of products. And there's a lot we can do with additive manufacturing in orthopedics. Crucially, we are in a lot of instances much cheaper than traditional implants. We can also change the modulus of things, so to better approximate the bone, so to make it more compatible with all the surrounding things, for example, to minimize stress sharing and stuff like this. And we can also, through geometry, we can change properties and change local properties as well. And we can quite effectively kind of print newer versions of things, iterate, and make things more effective quicker. And we can also do things like have optimal geometries, optimal textures for bone adhesion, other kind of properties. So I think this is a huge area for us. It's also an area where quality pays, where we need to have really good machines, really good powders, really good processes to make the same implant incredibly well at incredibly high quality every single time. So it's a beautiful area for us to pay attention to. Next is the Eggshell Pavilion, which we've on 3dprint.com. We've mentioned it before. We've talked about it a couple of times. These kind of these developments, they're taking place at ETH Zurich, and along with Gramazio Kohler, which is an office of architects. And what they've done here is, well, the stuff that gets the headlines is like 3D printing construction on site, right? And 3D printer constructs house in 24 hours is the typical headline. But actually, printing on site is actually kind of problematic because you either have to bring with you a giant structure, you have to build up there temporarily, or you're basically subject to a lot of problems with atmospheric variations in humidity and pressure, maybe to a certain extent, but also rain and stuff like this, and leaves getting in your print. So actually, like for a lot of things, we're seeing that printing in a factory is actually much better technology if you can do it, and then to drive the parts to the location. Another thing is that direct 3D printing is always going to capture our imagination a little bit more. But 3D printing of formwork is something we're seeing more of, and I think is much more is also really important and is really kind of underreported. And what happens in this case is that the ETH Zurich team managed to, you can see it here, using a robot arm, print 3 to 5 millimeter thick formwork out of PETG, GF reinforced or glass fiber reinforced PETG, which of course we all know because from the desktop printers, this is really a relatively inexpensive material, especially if you're laying it down 3 to 5 millimeters thick. Now they printed these really big panels, which you can see here, the top panels, that took 16 hours, and the columns, which are below them, that took 6 hours for all 4 columns to print. In that case, we can already tell this is a quite inexpensive component. And then what they did is they used 2 different kinds of concrete material to cast inside this formwork. They then used regular steel reinforcements. Again, I like the idea. These guys aren't doing stuff to like grab headlines. They're doing whatever makes sense. And of course, making regular steel reinforcements is a lot cheaper. Especially in this case, this pavilion has been installed at the Vitra campus, furniture, a well-known furniture company, and it's meant to be taken apart. It's meant to be temporary. So then using the steel off-the-shelf components really makes sense. The formwork itself can be recycled. So after using it for this particular thing, they can then grind it up and extrude it again and use it again to a certain extent, of course, as we know. But I think this is a really important development. If we look here, as like think about this, this is the formwork here. We can see that the print is not exactly stellar, but at 3.5 millimeters around this whole thing, this is really very little in terms of material. On top of that, it doesn't require a whole bunch of people running around with a whole bunch of wood. We would expect it to use less material, use less time, and be more automated. So I think this, of course, we're going to be drawn to the headlines: 3D print a house in 24 hours. But using reinforced PETG in this way is really exciting. Now, this is compounded by the fact that we can use the same reinforced PETG materials to make certain structures if they're lightweight. Think of like a balustrade, or think of like even like maybe some cases a footbridge and stuff like that. And so we can use very similar materials to do this. And on top of that, PETG is a material we could, of course, recycle from things like plastic bottles. So I think that's very exciting. Another bit of environmental news comes to us from Evonik. So Evonik, the polymer company that is essentially leading the powder bed fusion market, any kind of powder and additive, and has been for a really long time, has reduced the CO2 by half in its PA12 component. Now, this is actually quite big news because we run on Evonik PA12. It's still the default material for much of what you see that's 3D printed, especially in an industrial setting. This material also you can recycle it to a certain extent, and then you throw it away eventually. Like we throw away, it depends on who you are or what you're doing, but we throw away about half of this material generally. Some of it you can use more, and some of it, depending on the geometry and stuff, you use less. But just so the energy that goes into this material and the energy that we use is really quite significant. Everyone's always talking about 3D printing isn't environmentally friendly. Yes, to a certain extent. But not always, and we need to reduce this thing. So I love this move by Evonik. What I also really liked is that they're implementing this right now in their SLS, HSS, and MGF technology. So at one point, just the CO2 you buy from Evonik will be less per kilo of powder you buy from them. They're not going to offer a premium grade of this, or they're not going to say, oh, we offer it, and then there's some niche product. They're just going to switch their entire powder product portfolio to a more efficient production process. The product also uses renewable energy made at their site. This, of course, points to something that's going right now with really high gas prices in Europe. Gas is a really nice material to run an industrial facility on. A lot of people are looking to renewable energy, not only as like a cuddly, cute thing, also maybe as something to really make their products more survivable, if you will, in the world by insulating them from energy prices, energy shocks. They also say that they did a life cycle assessment on the material, which is always nice to hear, and it says that it came out quite positive with the Evonik Terra material. So Evonik Terra is a family of materials that uses castor bean oil or castor to make polymers. This is also similar to what Arkema has, real sun. This is also like a castor oil or castor bean derived product. So this also points to a couple of different things here. Like imagine you're using an industrial product and wind farms or whatever to produce CO2, or you're doing something like, made from castor beans. Like if you say made from castor beans, people automatically assume that it's absolutely wonderful and then nothing go wrong. This is part of the whole dilemma why everybody loves PLA. Maybe thinks it's a bit too safer than it is, and a bit too more environmentally friendly than it is. But of course, reducing these embedded energy costs and reducing the process energy that goes in it and making that process greener is additionally also a really positive development. And we're going to have to learn to differentiate as consumers, as companies who consume, between what's green. Like, is it green because it's plant derived? Is it green because of how much energy is in it? There's no standard measure for this, right? There's no bureau that certifies all this, or that we can't really measure a lot of these green claims against each other. Now, this seems legitimate, so I think that's wonderful. It's not like a greenwashing thing. It's like a legitimate thing that they're trying to do to offset CO2 embedded in their product. And I think I think that's a good development. I think, of course, and other people, this will lead to other people doing the same thing and people asking about what other products are like. So I think, to me, this is a really, really good move and really, good news for once. It's wonderful to have some good news. Thank you very much for listening to this edition of the